Hello class, good morning. This is the video for section 4.1, and chapter 4 talks about applications of differentiation. In fact, everything that we have learned, all the rules, we're going to apply them to real life situations. Okay, so 4.1 talks about the maximum and minimum values. Okay, there are two types that we're going to look at as we see in our um, objectives. We have to calculate the absolute maximum and minimum values, okay, and distinguish between the two, and then also local maximum and minimum values of a curve. So we distinguish between the absolute maximum and the absolute minimum and local. So what is absolute and min? What do we mean by that? And also find the critical values of a function and what occurs at the critical values of a function. Okay. And then, so some of the most important applications of differential calculus is what we call the optimization. Okay. You optimize a problem in which we require to find the optima, or the best way of doing something. Okay. So these can be done by finding what we call the maximum or minimum values of the function. So optimization basically talks about finding maximum or minimum. Okay, if I'm producing things, how do I maximize minimize cost and then maximize profit? Okay, if I'm given a certain material as an engineer to create a sheet or a disk, okay, how, small amount, can I maximize that material that's given? Okay, so that's what this is talking about. We're going to apply this to a lot of situations. All right, now as we can see from this graph, right, this is a graph and it's between a certain interval, okay? As you can see, it's between what, 1 and then it's a 7, okay? So we are given this interval of 1 and 7. Now in this interval, this is the curve. Now, this point, you see that is what, that's a maximum. So here there's a maximum point. Okay, and over there's a minimum point. All right, now you can see that what is the S value there? This is 3, and that is what? That is 6. So f of, at this point, what is f of 3 is equal to what? 5. And the f of 6 is what? Is 2. So we'll say that this is what the maximum what? Maximum value. Okay, and that is the minimum what? Minimum value. All right. So it is the largest value over the interval 1 to 7. Okay, and then that's 5, and then 2 is the minimum value or the smallest. All right, so let's define this, that a C, if you let C be a number in the domain of the function, okay, and then if we find f of C is what? It could be the, what we call the absolute maximum value of that. If it happens to be the what? The largest value over all, for all x in the domain of what? In the domain of D. So that's what we mean by f of C is greater than or equal to any function value in that. And then on the other hand, the minimum value, it is the f value, it is actually less than, okay? It says to be less than or equal to function value for all x in the what? In the domain, okay? So that is absolute minimum and absolute what? Maximum, all right? Now, what do we mean by that? This is sometimes called the what? The global maximum or minimum value. Now global because it is the what? The largest or the highest point or the lowest point over the entire domain of the function. So if a function is defined between negative infinity to what? Positive infinity, and we pick the highest point is called the what? The absolute maximum. And the minimum point is also called the what? The absolute what? Minimum. Another value, a terminology will be what? The global. So if I say global minimum or global maximum, I'm referring to what? The absolute minimum values. Now, this is called the what? Extreme values of the function. Okay? Extreme values of the function. So note that it is over the what? Its entire what? entire domain. Okay, now, so we also have, and in that domain, there's also called local minimum, all right? So f of c is called the local minimum because what? It is what? Is it the lowest over, the lowest point for the small value of for x near c, okay, in the interval. Sometimes we give that's what c of d for example. Okay, so the function f has, if you give it a function, it has a local maximum and local minimum. So generally, this is the definition for that. So local maximum value of f, okay, if f of c is what is greater than any function value near x near what c, and then it is what the minimum if for less than equal to f of s when x is what near c. Now, in fact, what we are saying is that when you say true value, something true near c, we are talking about mean that that is a true on some open interval containing what the c. Okay, that is, we are saying that when we restrict the what the domain, okay, we have what we call the local what maximum or local minimum. So if I go back to this graph that we talked about here, now since the domain is restricted, of course, this function can go between what? The entire domain of what the function, all right? So we can say that within this restricted domain between 1 and 7, this would be what the local maximum and local min, okay? It can also be what? Absolute, okay? Absolute and min, because you can have both occurring at the same value of x. Okay, now let us look at this diagram. This figure shows that what is happening at these values. Okay, now look at the value here, the value of y at these points, and then at that point. Okay, if I consider the interval between a and e in this case, all right, this is the highest point, is the largest over that interval. So we will say that we have what? We have some absolute what maximum occurring at what? F of what? Which is the y value is what? F of d. Okay. Now, if I restrict, if my c is near what? Near the value of d, that can also be called what? The local what? Local maximum. Okay. So at f of d, we also have what? We also have the local maximum what? Value, which is same what? F of what? F of d. Now, on the other hand, we have what happens at a. Okay. This is what? The absolute what? Absolute what? Min. Because it is the lowest value of the function that occurring at the endpoint over the entire domain. Okay. Now at f of c, we have local min. So we have local min there. Okay. And then e, we also have what? Local minimum here. All right. So local minimum are the values f of 4c, f of 4, f of e. Okay. So absolute maximum, absolute min, and then we have for local maximum and local min. In fact, we also have a local maximum. We have it at what? At b also. Okay. So at b, there is what? Local maximum there. So this is also f of what? F of d. Okay. So this is the absolute, again, because over the entire domain, that is the highest value of or the largest value of the function. And then this is the smallest. All right. Now, I want to make a point that we cannot have local maximum or minimum occurring at what? At the endpoints over an interval. Okay. So we cannot, this f of a cannot be what? Local min, because it's at the endpoint. Making sense. All right. Now, let us apply this to this question. Exercise number 7 says that we want to sketch a graph of a function f that is continuous on the interval 1 to 5 and has the given what properties. It has absolute maximum at 5, absolute minimum at 2, local max at 3, and then local minimum at 2 and 4. So we're going to draw a graph. Sorry. Okay, we're going to draw our graph. Okay, now I have 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. And this is x, that is real y. So we want to sketch a graph. It says that there is we have what? Absolute maximum at what? At 5. So at 5, okay, we want to check that there's an absolute maximum at this point. Okay, it is inclusive interval, so it's going to be inclusive. Then we have what? Local minimum at what? At 2. We don't know the y value, but there's a local minimum that is like that. Because it said what? We have an absolute also, absolute minimum at 2. Because we also have, what do you call it? Local minimum at also 2. So that is why it's going to be like that. Okay. Now, it says that they have what? Local maximum at 3. Local maximum at 3. Now at 4 too, there's a local minimum. If this is also at 2, we have absolute minimum. The local minimum value at C, it cannot be below that. It has to be up. So at 4, we have something like that also. And at 3, we have what? Local maximum. So at 3, we have local maximum. So that's going to be like this, something like that. So if I want to sketch this graph, okay, between 1 and 5, it's going to be like this, goes up, and then local min, maximum, sorry, and then local min, and then what? Stops there. Okay, so this is the point. Okay, that is an example of that graph. So this is a graph of what? That satisfy what? These properties or conditions. All right, now let us define theorem. Okay, where we can find the what? Absolute maximum and minimum. Say that the following theorem gives a conditions under which a function is guaranteed to have what? Extreme values. Okay, and it says that, note the hypothesis says that f is continuous, okay, on a closed interval AB. It is continuous on a closed interval of AB. Then it attains absolute maximum value f of C at a certain point in that interval C. It has absolute also minimum, okay, f of D at that point. Okay, so and where the C and D are in the word in that interval, they cannot be outside. Okay, so graphically, if I have A and B defined over A and B like this, okay, here there's an absolute what? Maximum. Sorry, absolute max. And then over here, there's what? Absolute what? Min. All right, now if I consider this here, there is what? Absolute max. And over there, when D is equal to that's what? Absolute what? Absolute min. Okay, if I consider this diagram, these are possible diagrams. Okay, these 2 points, okay, they are the same. So in both cases, we have what? Absolute max. Okay, we've got the same value. And then we have what? Absolute minimum at these 2 points, if they are the same. Okay, there we have what? Absolute min. So this extreme value theorem says that if a function is continuous, as you can see, it's continuous in each of the interval AB for each of the graphs here. And there is, you can guarantee what? Absolute was maximum and absolute minimum over the interval. Okay, now, is that happens? Right, let's look at these 2 graphs. Okay, now consider the graphs and answer the question. does the graph contradict the extreme value theorem and why? Okay, now as you can see, this graph, figure 9, okay, it has, this is the absolute word minimum. It has a minimum value, okay? There's absolute minimum, or you can say, just say that it's a minimum value, but it has no maximum because this value does not exist. So no max, okay? Now, does it contradict the theorem? The answer is what? No, okay? The answer is no. Why? Because the function is not continuous on the interval, what? In this case, the interval 1, 2. Now the second one, we know that it is continuous. So the hypothesis of the word function is defined. This is defined over the interval. What is it? The interval is from what? 0 to what? To 2, not inclusive. So it's parentheses. Okay. So the question is that this interval is not closed. It's not a closed interval. Sorry. It's not a closed interval. Okay. Now, it is continuous. It doesn't have maximum or minimum. No maximum or no minimum because this does not exist. That's continuous. This keeps going. Hold me back, please. Sorry about that. Okay. So this also does not contradict what? The theorem. So the answer is no, because this is not what? The interval is not what? It's not close. Okay. Okay, so now let's continue. It says that we want to look at also local maximum or local minimum values. Now, another name for local is what? Relative. Okay, so here relative maximum, relative minimum, we are referring to what? The locals, okay, extreme values. So this theorem is called the Fermat's theorem. Now, it says that a function f has a local maximum minimum at C if we differentiate a function and set it to what? And set it to 0 and evaluate it at C. Okay, then if it exists, then this is true. Okay, now what that means is that the slope of the tangent line is horizontal. Okay, because this only happens when the what? F prime of x is equal to what? 0. Now, as you can see in this graph here, at these points, C and then D, all right, the function is what? The tangent line is horizontal, okay? It's horizontal at both, okay? These points. Now, if it is the case, then what is happening is that this Fermat theorem said that there's going to be what? A local maximum or local minimum. All right, we can say that this is a local as this graph is defined. But is that always the case? All right, that if you set f of x to 0, and then if you f prime at C is equal to 0, if you set that, it's always the case. So there are certain cautions in using this theory. Now, in the following cases, I call them remarks. Okay. Now, first remark is that don't read too much into Fermat's theorem because we can't expect to locate extreme values simply by what? Setting f of x to 0 and solving for what? X. Okay. Now consider this example. Consider the function x cubed. X cubed is this graph that we have there. Okay. Is that graph. Okay. So then let us differentiate this. If you differentiate the function, you get 3x squared. And then what is f of prime at 0 is what is 0. So we are saying that at this point, we have what? We have what? Local maximum or local minimum, which is not true, because here we cannot tell, all right? We can't tell, okay, whether we can't tell whether the function what. We can't tell whether the function has what? Local maximum or local minimum. So it doesn't have. And yet f prime at 0 is equal to 0. So we could say that this is what? Minimum value or maximum value. We can't tell. So it doesn't, that's why I said don't read too much into what? The Fermat's theorem. The second thing is that it is saying that we consider this absolute value function, okay? F of x is equal to absolute value. So there may be even extreme values of f when simply simplifying by setting what? F of prime of x does not even exist. Okay, we know that f prime at 0, okay, in this case, it does not exist, all right? That's not what exists. We proved this. We proved this a while ago in what? In chapter 2, okay? So we know that this value should have been what? The minimum value, but we know that f of 0 is what? Is a minimum value, okay? It's on, and the value near 0 is your minimum value. It could also be what? The absolute value, but it doesn't work. It doesn't exist. The f prime there doesn't exist. Okay, you cannot even find this, let alone, okay, setting this to 0. It's not possible. All right, so that's the second case. Then the third one leads us to a definition. Okay, so Fermat's theorem does suggest at least that we should at least start looking for extreme values of f that at the number c, where when we equate this what? We differentiate and set it to what? And set it to 0. Or where that function at c, the derivative at c does not exist. So this number c, we are giving it a special name. And that's what we have for this definition. It is what called the critical what number. So a critical number of a function of f is a number c in the or is domain of f, such that the f prime at c equal to 0 or f prime at c does not exist. Now, in terms of Fermat's theorem that we talked about, we can rephrase it as the following: that if f has local maximum and local minimum at c, then c is what's a critical number. The c is a critical number. And therefore, we can use combination with this definition in the Fermat's theorem, where we consider where this two, okay, f prime at c equals 0, and then or it doesn't exist, to find the what? Local maximum and local what? Minimum values. All right. So here is an example. It says that find the critical numbers of the function. Okay. All we need to do is that we have f of x. So the solution is this. Okay. Let's find f prime of x and set it to 0. Okay. F prime of x is what? 6x squared minus 6x minus 36 equal to 0. Divide through by 6, we have x squared minus x minus 6 equal to 0. Now let's factor this. This will be x minus 3, x plus what? 2 equal to what? Equal to 0. Now that means that, x is either what? Equal to 3 or x is equal to -4, -2. Therefore, in this case, these are the critical numbers. So my critical numbers, or sometimes we call critical points, are x equal to -2 and then 3. That's it. Okay. Well, here we know that f prime of x, okay, at -2 exists. Okay. And it's what? And it's equal to what? 0. And then f prime at 3 also exists and what is also equal to what? Equal to 0. Okay. So now, is there anywhere this function does not exist? Okay. No, there's none like that. There's none like that. Okay. Here's another example. I use a trig function. So we have f of theta equal to that. Now we want to find the critical word numbers for this function. So first we want to find f prime of what? Theta. In this case will be minus, that's minus 2 sine theta. And then we have plus 2 sine theta using the chain rule times what? Cosine what? Cosine theta. Now we want to set this to 0. Okay. Now if you set that to 0, then we're going to have minus 2 sine theta plus 2 sine theta cosine theta equal to 0. Now let's factor sine theta out. Okay, that's 2 sine theta. All right, we have minus 2 sine theta outside, and then we are left with what? Just 1 minus cosine what? Cosine theta equal to 0. So we're going to set both to 0, minus 2 sine theta equal to 0, or 1 minus cosine theta equal to 0. Okay, this is, so first we want to find what? Divide both sides by 0. Negative 2. Okay, you have sine theta equal to 0. This is over negative 2. And then you have here, you're going to have cosine of theta equal to 1. Right? So then the angle is what? The arc sine of what? 0. Or theta is equal to what? Cosine, arc cosine of what? Of 1. So we want to find the angle whose sine is what? 0. Now, as you can see, we will know that this will be what? 0, pi, 2 pi, okay, 3 pi, and so on and so forth. So generally, this is what? N times pi, where n is what? An integer. Okay, n is what? Integer. Okay, now over here too, theta is equal to, if it's equal to 1, it is also 0. Okay, and then even 2 pi. So go around 360 again, 4 pi, and so on and so forth. Okay, which we can generalize as what? 2n what? 2n pi. So in this case, the solution will be, the solution to the equation, we have what? Theta is what? N pi. Okay, this includes all the what? The angle theta equal to what? Theta equal to 2n what? N pi. Okay, so therefore your critical values, the critical values are theta equal to what? N pi. Okay, again, n is what? Integer. Okay, so we have that. Very good. So that is 2 examples. Find the critical values of a function. All right. Now, final thing is that finding maximum and minimum values. Okay. So to find the absolute maximum and minimum values of a continuous function, right, on a closed interval. So something like that. Okay. We know that either it is a local or it occurs at an endpoint. So we can have, like, remember I said that we can never have the absolute extreme values occurring at the endpoints over an interval. Okay, can never have that. Sorry, the locals. I misspoke. You can never have the local extreme values occurring at the what? endpoints, but you can have what the absolutes. Okay, so this is a method, the closed interval method, to find absolute maximum and minimum values of a continuous function over a closed interval. First, find the values, okay, of the critical numbers. So that means find the critical numbers and find the values, find them. Then evaluate the function, okay? Evaluate the function at what? The endpoints, okay? And also at the what? At the critical value or numbers. Then the largest of these values in steps 1 and 2 will be the what? The absolute maximum, and the smallest will be the what? Absolute minimum. Now notice that we just concluded that if I have a critical number, I can have what? Local max and then local what min. Okay, but these are these values where we have the critical numbers of x. We can also have what? The absolute what? Maximum or absolute minimum, depending on whether it's the highest or the lowest. Okay, so here is example. Okay, we have, this is a polynomial function. It's a polynomial, and so if it's defined over a closed interval 0, 5. So all that we need to do is that we need to find the step 1 of what we just said, that find your critical values and evaluate at that point. Okay, so I'm going to find just the critical values. So differentiate this and set it to 0, 0. So this gives me 4 minus what? 2x equal to 0. And that implies your x is equal to what? 2. Okay. Is 2 in the interval 0, 5? Yes. So this is what? This is a critical what? Value or critical number. It's a critical number. All right. Now, I will evaluate them, but I'll put them in the table. Okay, so that we can. Now, let us find what is f of what? F of 0. So in plug in 0, you have 12 plus 4 times 0 minus 0 squared is what? Is 12. And then what is f of 5? Okay, this is your f of a. F of 5 is 12 plus 4 times 5 minus 5 squared. Okay, if we evaluate that, we get what? We get 7. And this is my what? F of what? F of b. So I'm going to put this in the table so that we can decide. It's easy that way. All right. So this is my x value, and this is my f of x value, right? So we have 3 of them. We have it at 0, and then 2 is a critical number, and then we have it at 5. Now, when x, we have to evaluate. Let's find f of 2. F of 2 will give us 16. F of 5, it's 7, and then this is what? This is 12. Okay, so this is the largest value. Therefore, what is your absolute maximum value? It is what? 16 at what? X equal to what? 2. Now, because 2, okay, since 2 is critical number, okay, it's 16 is also what? The local max. Okay. Now, this is the smallest. So this is where we have what? The absolute what? Min. So if you summarize that, the absolute min or absolute max, let's put that absolute and local max is what? 16 at 2. Okay, and then they have what? Absolute what? Min is what? Is 7 at 5. Okay, and then finally, this is also a trig value, a trigonometric function. So step 1, Okay, we find f of t is set to 0. Okay, so if we differentiate that function, what do we get? If we differentiate this, we have, this is what, minus 2 sine t, okay? And then it's going to be plus 2 cosine 2t. Now let's set this to 0, okay? Now, let us know that I cannot solve a question like that when I have different trig functions. It has to be only one of them. So I look at cosine 2t and express it in terms of sine. Then that is what? That is given by 1 minus 2 sine squared what t. And then this is minus 2 sine t. So this becomes a quadratic function. When you multiply the distribute the 2, you have what? Minus 2, sorry, actually minus 4 sine squared t minus 2 sine t, then plus what? Plus 2 equal to what? Equal to 0. Okay, if you multiply through by what? If you divide through by 2 and negative 2, this will give me what? Just 2 sine squared t, then plus what? Sine t minus 2 equal to what? 0. So if we solve for this, this side, if we factor, we have these factors. This will be 2 sine t minus 1 times sine t plus 1 equal to 0. So we have two functions, equations there. 2 sine t minus 1 equal to 0. Or we have sine t plus 1 equal to what? 0. Okay, so let us solve this. We equate it to 0. This will be sine t equal to 1/2. So t is equal to the sine inverse of what? 1/2, which will give us pi over what? Over 6. Now, on this side, you have what? Sine t equal to -1. And t is equal to the arc sine of what? -1. And that will give us this 3 pi over what? Over 2. Okay, because pi by 2, sine pi by 2 is 1. And then that's the 90 degrees and 270 degrees. Okay, that's what we have there. But you see that this is not in the domain that is given. It's not in this domain. Okay, the domain is what? Is defined for what? 0 and what? Pi by what? By 2. It's not in the domain there. Okay, so let's put all together and get a table. So this is the only what? Only critical number. So I'm going to put my table, all the 3 steps in one. My x, so this is t, and then we have what? 0, pi by 2, and then we have 3 pi by 2. Then we make it a 6, and then pi by what? By 2. So let's find f of t. Okay, if you substitute 0 into the function, original function here, okay, that is 2 plus what? 0, which is what? This will be 2. Okay, then if it's pi by 6, evaluated, you get 3 root 3 over 2. And then if you substitute pi by 2, cosine pi by 2 is what? 0. And so you only have sine pi 2 times t. So that's just pi. And that is going to be what? 0. Now among this, which is the largest value? Okay, so we have what? The absolute, this is the greatest value. This is greater than 2. So the absolute max is what? 3 root 3 over what? 2 at pi by 6. And it is also local, okay? Local max, because this is a critical number. And then the absolute mean is, that's what? 0 at pi by what? 2. So that actually brings us to the end of what this section. We'll do more examples in class. Thank you.